A variation of the mask would be to apply a binary clip using multiplication. So here we've got example rasters, an input, a clip raster, and an output. The input has values of some kind, something that does with the cell values. We don't have to know what they are. The clipping raster is ones and zeros, and so this is one that you can create using standard map algebra if you need to, or reclassing information. You can reclass everything that you want to keep. All the cells that you want to keep become ones. Everything you're not interested in becomes a zero. So we multiply these two rasters together, the input times our binary clip, and we get an output raster where all of the values or all of the cell locations that we didn't care about become zeros because we've multiplied them by zero, and all of the cell locations that we wanted to retain their values, and there they are. They're kept, right? So here's a great example of how we can use that basic multiplication as a clip. The best way to probably create your clip raster, if this is an approach you want to take, would be to simply reclass whatever it is you want to use as the clipping raster. Okay. So the ones in the clipping raster retain values in the output. The zeros blank them out through multiplication. So the reclass tool, appropriately enough, here we go. We've got slope. We want to class the slope into two slope classes. We're only interested in, let's say this was in degrees. So our input raster slope has degrees 0 to 10, 10 to 90, and we only want 0 to 10. So we reclass that as 1. Everything else we reclass as a 0. And, you've created something here that's a little bit familiar. This is a Boolean output where we have 0 to 10 is true, 1. And then the range greater than 10 to 90 becomes 0. So reclassing is something you would use probably not for something this simple, but for a more complex raster that has many values in it. This is a quicker way to go about doing that, and especially if you need to combine different numeric codes that are coding for categorical information. Boolean analysis won't get you there very easily because there you're doing a condition that's assuming it's a mathematical relationship. But if your values in the raster actually code for categorical information, reclassing is how you can create a Boolean logical data set from that original input. Okay, so there's why reclassify. Because sometimes your data sets will require that approach rather than a simpler Boolean approach. So now it's time to make raster analysis just a little bit more complicated by examining different scales of raster analysis, local, neighborhood, and global. The local scale is what you've already experienced in lecture. We've covered it quite a bit. It's cell by cell map algebra with a single cell input and a single cell output. So we apply an operation to every cell in the input grid, and that becomes the output in the output grid. Neighborhoods are when we create what's known as kind of a window or a spatial filter. We specify a size for that, usually an odd number of cells, so 3 by 3, 5 by 5, 7 by 7, as a window of that number of cells. And then we apply some sort of mathematical, statistical technique to that window. If it's a spatial filter, like we use in remote sensing, we may have different values throughout those different cells. But in general, what we're going to do in ArcGIS We'll use the example here. Let's talk about focal neighborhoods. So multiple cells used for calculation of some kind with a single cell output, a target cell in the output raster. So the example here, we have a 3 by 3 window. All of the cells from the input grid are used in the computation, and the result of that computation or calculation then gets transferred to the target cell, single cell in the output. With a focal neighborhood, then it's a traveling window, and it moves by increments of one cell at a time, creates a new neighborhood of, in this case, 3 by 3 neighborhood of cell values in the input raster to calculate the corresponding target in the output cell or the output raster. So with a neighborhood maximum, a focal neighborhood maximum on a 3 by 3 unit of analysis, it's going to pick the maximum value in that particular selection of 9 cells, which then becomes the output in the target cell. And as it moves, it changes the input cells and therefore the output. And so that's any calculation that you use or any query that gets applied using a focal neighborhood works that way. A block works a little bit differently. A block uses a specified window size, 3 by 3, 5 by 5, 7 by 7, whatever it is. But the output is put into the same size neighborhood in the output data set. So for example, if we were to use that same middle example, instead of, if it was a neighborhood maximum, a 3 by 3 input, there the maximum value would be 42, and 42 would be written to the corresponding 3 by 3 window in the output grid. So this results in really blocky information, whereas the focal window creates a smoother surface. Okay, we'll see some examples of these later. A global function uses the entire array at once to create the output. So a global maximum for the entire raster input creates an output of that maximum. And if it was addition, it would be the same thing. If it was a mean, it would be the same thing. It applies it to all cells in the output. So using a focal neighborhood, here's an example graphic showing us a sample 3 by 3 neighborhood and some of the things that we can query from that using statistical tools and neighborhood tools. Given those values in the 3 by 3 grid in the center, calculate a mean that gets written to the target cell, a median value, the minimum value, the range between high and low, the maximum value, the majority, which means the number that occurs most often, calculating an aspect. Imagine if those values out there were elevation values. So what's the aspect of the target cell? And what's the slope of the target cell? So those things that we've created before are actually being computed using a neighborhood function in a moving window, a moving focal window of cells. And as that window progresses through the input raster, it computes using that specified window size, in this case 3 cells by 3 cells or a 9-cell array, to compute in the output layer the target value, depending upon whatever technique we are allowed to use by the software or that we program in using a programming language, will determine how our neighborhood works and what its output values are going to be. Now here's another example of a moving window and a kernel or spatial filter. We've got a 3 by 3 moving window for the neighborhood, and it operates on that 9-cell neighborhood and puts an output into the target cell in the output data set. The kernel in this case, each cell value, we can specify in some software the values of each particular cell in that kernel or spatial filter. They don't always have to be the same value. They don't always have to be positive. They can be negative values as well. And in this case, what the kernel is doing is it's applying the function of multiplying by 1/9 the value of each input cell and then summing those. So 13 divided by 9 plus 12 divided by 9, etc., etc., etc. Add all those things together and you get 11.1 as the computation based upon that 3 by 3 neighborhood, the operation of input cell value multiplied by 1/9, which is the same thing as dividing by 9, and then summing all of those values. So you can program a kernel or a spatial filter in your software, depending on what its capabilities are, to do a variety of different mathematical functions to those cells in the input neighborhood. And there are a number of those, quite a few, that exist. There are things that you'll probably run into in more advanced GIS or remote sensing classes where they're more appropriate to discuss. But anyway, the thing to remember here is that you've got a moving window. In ArcGIS, typically the things that we're going to be doing are going to be fairly simple. In this class in particular, fairly simple operations on that moving window that give us a single output value in the output raster. One of the problems that occurs with some of the operations that we can do with these moving windows is that we can enhance what's known as spatial covariance or autocorrelation. Because we're using that moving window in neighborhoods of cells that are close to each other, each successive calculation has a lot of cell values in common with the previous calculation. So in essence, we're creating an output data set with some of the functions that we can call up and use, where the values tend to be closer to each other than they were originally. So we're increasing the similarity between the numbers. In spatial terms, that's known as autocorrelation. How similar is one, in this case, pixel, to the next adjacent pixel? Some of the operations like the arithmetic mean, the average function, will tend to create things that are more similar to each other. So we're increasing the amount of autocorrelation. And that may be something that we're interested in the output. That may be great. It may be something that we're not so interested in. This is a concept that has applications in certain kinds of statistical analysis where we want to be concerned about if autocorrelation exists, how much does it exist, and is it something that's going to really skew the results of our statistical analyses. So for here, in this class, this isn't something we're going to explore in a whole lot of detail, but it is something to be aware of as you move on in more advanced GIS and remote sensing courses and training, that applying these spatial filters, these focal neighborhoods, to our data sets, we are increasing the amount of autocorrelation. And another reminder, resampling is fundamental. It's a problem. It's something we need to get a control of in our raster-based analyses. And for one last time, the best practice is to do that first. After you assemble all the data sets you're going to be using in your analysis, decide on a common projection, figure out what the coarsest cell resolution is, reproject and resample to match all those things together so that your input grids, as much as possible, are matching each other spatially. And that will give you better results in the end rather than relying on the system to do things on the fly in the background. That will, over time and over multiple operations, insert more error in your output calculations, computations, insert more error, therefore, in your results. So, we want to minimize error as much as possible in our analytical routines. So our best practice is take care of those things first. Reproject, resample, get your data in order prior to doing any other type of analysis. So let's finish out general raster analysis by looking at another example of selecting a site for a landfill. So our problem is we want to find potential locations for a new landfill using particular criteria. On flat terrain, less than or equal to 10 degrees of slope, no more than a kilometer from an existing road, at least 500 meters from a stream, and located in a meadow or low-density forest. So from our input data sets, our rasters, we will develop Boolean rasters for each condition, with a 1 meaning true, meaning desirable characteristic or condition for our landfill, and 0 is not desirable, not what we want, it's false. So for the slope condition, we have an input raster. We apply the appropriate query using the raster calculator to find slope less than or equal to 10 degrees, and we have then our output. 1's where it's true, 0's where it's false. For the road distance condition, we have a vector data set of road locations in space. And so we're going to use that first to create a distance grid. Then we use the Boolean operator, the logical operator, in the raster calculator to select cells that are within 1,000 meters of a road. So we've got on the left there our vector data set, in the center the distance raster data set, and then on the right our Boolean output, 1 being green, 0 being gray, true and false. Stream distance condition, again we have a network of lines describing the streams. We need to create a distance layer first, so we create distances from the streams. That's in the center, and on the right we select from that distances greater than 500 meters. In this case, 1 is true, purple, 0, gray, false. To find our land cover type, or in this case the vegetation condition, we're selecting from the data itself a measure of that, the vegetation density, as a proxy for meadows and sparse trees on the landscape. And so we convert the polygons to a raster, recode them, reclassify them, and that produces 1's and 0's. 1's where we have meadows and sparse forest cover, 0's where it doesn't meet that condition at all. So then we combine these using our Boolean, more restrictive analysis for slope and roads and streams and vegetation. And remember that that's basically multiplication. So 1 times 1 times 1 times 1. And all the zeros fall out. So our potential sites are the ones that are shown in brown, and everything else is gray. So this is the most restrictive analysis that you can do by using Boolean, and these are the cells, the locations in our data set that meet all 4 conditions at the same time. If we approached it the other way, the additive approach, or creating a ranking or a score, we add them together. Slopes plus roads plus streams plus vegetation gives us potential raster cell values in the output from 0 to 4. 0 meaning not appropriate, 1, 2, and 3 marginal but increasing in suitability, and 4 the most suitable. 4 is the same result as the Boolean AND approach. 4 is the most restrictive. 4 must have all 4 conditions met for each cell. And the other ones are decreasing in suitability as you count down to 0. Okay, so here's just a quick little example, expanding upon the landfill siting example used earlier in the lecture. But there's a lot of different transformations that we need to do to the information. We didn't go through all those steps at all. The techniques and the actual commands that you would need to use, and all of the different choices for those commands to produce the rasters. But in the end, we have those raster outputs in ones and zeros, and then combine them in different ways to decide where's the most appropriate location or potential appropriate locations for our landfill site. This is a kind of analysis that's quite frequently done in many different professions and career paths, is doing suitability analysis one way or the other, using either vector data or raster data or both to arrive at those conclusions. And that's where we're going to end out with our general discussion of raster analysis.